Lighting calculations need surface normals in order to determine the angle at which light strikes each point on a surface. To get surface normals, you take the vertex points / normals of the triangle and interpolate them across the triangle during rasterization. To find a normal of a triangle, we find the two vectors on the triangle's edges, then face normal is equal to those vectors multiplied by each other. Interpolating the normal and doing lighting calculations per pixel is called Phong lighting, which we can see being calculated here. A different way of doing this is doing lighting calculations per vertex, which is less expensive but is also less accurate. Diffuse lighting is how when light hits a point on a surface, some of the light enters the interior of the object and interacts with the matter at the surface. Light will reflect around the interior, with some of it being scattered off the surface and some absorbed. This is referred to as diffuse reflections. Diffuse lighting is calculated using the amount of incoming light multiplied by diffuse albedo, which is the amount of incoming light that the surface will reflect, which you can see being set for the skull here and other materials. As well as multiplying incoming light and the albedo, Lambert cosine law is also used, which controls how much of the original light the surface receives based on the angle between the surface normal and the light vector. A second type of reflection called specular lighting occurs due to the Fresnel effect, which we can see the calculations for here. This is when light reaches the interface between two media with different indices of refraction, where some of the light is reflected and the remaining light is refracted. For opaque objects, the amount of light that reflects off a surface is a combination of diffuse light and specular reflection. Surface roughness affects this as well as diffuse lighting. Ambient lighting, which you can see being set here, uses indirect lighting to uniformly brighten a scene, with the idea that the indirect light is scattered and bounced around the scene so many times that it strikes the object equally in every direction, and you can see without it that the scene is completely black. An example of this being used in a game is a hallway being lit up from a light source in an adjacent room. Roughness affects how light is scattered from an object. For instance, smoother surfaces like polished metal, you would want a lower roughness, and for something like concrete, you'd want a higher roughness, as light will spread out more into a specular lobe. Increasing the roughness increases the number of microfacets, which are tiny flat elements on the surface of the object that reflect light away in different directions, away from the macronormal, increasing the specular lobe with the opposite when roughness is decreasing. You can see here that if I lower the roughness for the skull, it becomes shinier. You can see the roughness factor being calculated here in the Blink-Phong method. Directional light, which I've set here, approximate a light source that is very far away, with incoming light rays being parallel to each other. Because the light source is very far away, distance can be ignored, and only light strength and a direction vector need to be specified, which you can see. An example of a directional light in the games is the sun, as it's far enough away for rays of light to be almost parallel. I've used the sin f function with total time to create a disco-like effect. This function is also good for making an alarm light effect in games. You can see the directional lights being calculated here. Point lights are lights that radiate light spherically in all directions. You can see the green light positioned here is radiating light at the spheres and at the skull. Because of this, the light vector must be calculated for each point as it varies from point to point, whereas with directional light it remains constant. It also means that point lights don't need a direction, but they do need a position. A good example of point lights in games are light bulbs, and we can see the point lights being computed here, as well as the light vectors being calculated here. Spotlights radiate their light in a cone shape in a set direction from their point of origin, in this case toward the skull, with the light in the centre of their cones being more intense than the outside of the cone. A good example in the games of spotlights is flashlights, and you can see the spotlights being computed here in the pixel shader, as well as their attenuation, which scales the light strength down linearly after fall-off start until it reaches 0 at the fall-off end. This is useful to optimise lighting calculations, as if a point is past fall-off end, it can be skipped. You can see that I've had fall-offs to this red spotlight, reducing the light's intensity before it reaches the skull. Attenuation of fall-offs can also be used on point lights. Lighting is additive, which means we must iterate over each light source and sum its contribution to the point we are evaluating. Here you can see each light type adding more light to the scene. For ambient lighting, directional lighting, point and spotlights, adding more to the light intensity. We can only use up to the max lights amount defined as 16 here in the pixel shader, and you can see the order the light types come in and the amount set for each set here. We can also see the light types being computed and accumulated here in the pixel shader, with each light type being iterated over.